In this podcast, we'll discuss Taylor series methods for differential equations. The previous podcast we discussed Euler's method, which is the simplest method and is based on using Taylor series up through the first order term, letting big Y of x plus h, the exact solution, that is equal to y of x plus h times y prime of x plus more terms. With Euler's method, we only take through the linear term as our approximation. Now, we can take more terms of our Taylor series method when we're trying to solve the ordinary differential equation. Y prime is f of x and y with an initial condition y of x naught is equal to y naught. We could take as many terms as we want of the Taylor series, because we know taking more terms of a Taylor series gives us a solution that is better for a longer distance away from the initial point than if we were to take fewer terms of the Taylor series. The more terms you take, the better the approximation. However, finding these higher order terms is more difficult. We start off knowing y prime is f of xy, but what is y double prime? Y double prime is the derivative with respect to x of y prime, which is the derivative with respect to x of f of xy, because y prime is f of x and y. And that involves taking partial derivatives. That's f sub x plus f sub y dy dx, which is f sub x plus f sub y, and we plug in for dy dx, we plug in dy dx is equal to f. But the calculations become complicated very quickly. If we want to take the third order term, y triple prime, that's the derivative of y double prime, which is now the derivative of this mess that we have on the right hand side. And taking that derivative, we see that gives us 1, 2, 3, 4, 5, 6 terms. So the amount of work really grows the more terms that we take using a Taylor series method. Here's an example. Suppose y prime is equal to e to the minus x cosine y. And we don't even bother with the initial condition here. We just want to demonstrate how it gets messy very quickly. So y double prime is equal to f sub x plus f sub y times f, and we plug that in. F sub x is minus e to the minus x cosine y. F sub y is e to the minus x times negative sine y, and f is e to the minus x cosine y. So y double prime is a long expression. Y triple prime is much more complicated. If we let the approximate solution be represented by little y, then keeping the Taylor series terms through second order gives us y of x plus h is y of x plus h times y prime. That's what we have here. That's just f minus h squared over 2. The minus is because we have the minus over here. Just pulling that minus sign out. We have the h squared over 2 times our terms e to the minus x cosine y, and plus e to the minus x sine y times e to the minus x cosine y. And we put that all together, and then our single step error is order h cubed. It's related to the first term that we omit, which is h cubed over 3 factorial times y triple prime of x. If we work out one step of this example, letting y of 0 equal 0 and step size equal 1 to make it simple, we have y of x plus h is y of x plus h e to the minus x cosine y minus this h squared over 2 factorial term that we just discussed. And we plug in x is equal to 0, h is equal to 1, and the initial value of y of 0 is equal to 0. And so we plug in for all these values. All the x's are 0, all the y's are 0. And we work that all the way through, and we have y of 1 would equal to 1 after one step using the second order Taylor series method. So let's take a look at the global error order for the second order Taylor series method. Right, our single step error was h cubed over 3 factorial times y triple prime, somewhere in the middle. And that's because we took all our terms up through the h squared terms, and so the first term that we leave out is h cubed over 3 factorial. Once again, as we did in the Euler series, in the Euler method podcast, going from a to b with step size h gives b minus a over h steps, and the approximate error for the interval from a to b is going to be the error in one step, h cubed over 3 factorial y triple prime, times the number of steps, b minus a over h. That gives us a rough estimate. The h cubed over h brings us an h squared, and we find the overall error is order h squared. If we have the step size, then we would reduce the error by a factor of 4. So if in the previous case we took h is equal to a half, instead of h is equal to 1, we'd have to take 2 steps, but we'd reduce the error by a factor of around 4. And here's a moment of culture. Hopefully you can click on this link and you'll get the video and find out why 28 divided by 7 is equal to 13.